Hey, my name's Patrick, and this is Stats with Pat. Today we're going to be talking about the goodness of fit measures of linear regression. We're going to be exploring a little bit in R, but most of it's just going to be an analysis of those three goodness of fit measures. Let's get started.
I'd like to start by saying that for the duration of this video, I am going to be working under the assumption that whoever's watching it has at least a basic understanding of what linear regression is. I will make a video about linear regression in the future, but for right now, we're just talking about the goodness of fit measures. The three goodness of fit measures are standard error, R squared, and adjusted R squared. These are all put out in a normal linear regression, whether you're doing it in Excel or in R, but I'm going to go ahead and show you what it looks like in R. This is the standard error, which is the average distance for a particular data point from the linear model that we created. This is R squared, and it is the proportion of variation explained by the model's independent variable or variables. Finally, we have adjusted R squared, which is just like R squared, except it has been adjusted to account specifically for the number of independent variables being used to explain the observed variable. Now we can go to R and take a look at the code that we need to use to create a linear model that gives us a similar output that we just saw. This is the basic code that we would use to create the linear model and then to print a summary of the model. Here we're using data called insurance, and we're seeing how much of the charges variable can be explained by the age variable. When we run that code, this is the output that we get for model 1. And now that we know a little bit about what's going on with R and a little bit about the goodness of fit measures, we can go ahead and compare some of the models that I've created. If you look, the first three models are simple linear regression, and we know that because they each only have one explanatory variable. The next three variables are multiple linear regressions, which means that we're using more than one explanatory variable. We're going to take a look and see how adding more variables can make the model a lot stronger. If you take a look at standard error, each time a variable is added, generally speaking, the standard error decreases. We really want a low standard error because, once again, that's the average distance that a data point is from our model line. If the model that we created perfectly fit the data, then our standard error would be 0. There are some flaws with the standard error, though. There is no meaningful upper limit. It can go on forever. So using it as a standalone goodness of fit isn't really something that we can do. However, as you can see, comparing models against each other is something we can do. Obviously, between the explanatories sex and smoker has a much smaller standard error, which makes sense because obviously whether or not you smoke would have a way bigger impact on how much you pay for health insurance than your sex would. Now we can start talking about R squared. R squared is different than the standard error because it can be used in isolation. But you have to be aware that it can really only be used to compare models that have the same number of explanatory variables. Because regardless of how good a certain explanatory variable is, it could be the worst explanatory, just garbage. If you added it, it will increase the R squared statistic. The closer R squared is to 1, the better fit the model is. Now, it is still a relative statistic because if you're trying to predict like a response variable that is very challenging to predict, then something like a 0.25 R squared may be pretty good. If you found a combination of explanatory variables that can predict 25% of the response variable data, that's pretty good. But there are other situations where even a 0.9 R squared statistic may not be very impressive if it is for the model where the response variable is really easy to predict. So you really need to be aware of the context of the data you are analyzing to know whether or not your R squared is particularly good. But it is always helpful to use as a comparison tool between models, just as the standard error was. Lastly, we can talk about the adjusted R squared, which is just like R squared, but mathematically there is a penalty that is imposed for each additional explanatory variable that is added to the model. So when you're using when you're comparing two different models that have different number of explanatory variables, then adjusted R squared is the number that you want to use. So if we look back at our comparison, just as a final conclusion, which data set or which model is going to be the most accurate? In my opinion, model 6 is going to be the most accurate because our standard error is the lowest. R squared isn't super relevant because all of our models, within our models, we have differing numbers of explanatory variables. But if we look back to the adjusted R squared, it is the superior model. The fact that it's only a little bit above model 4 might indicate that children or the region that the people are from might not have a very big impact on the model. So it may be something that we consider throwing out altogether. And I know there are so many parts of the goodness of fit measures within a linear regression that I wasn't able to cover. So please let me know if there was something that I could have added that was maybe more relevant to people who are learning about linear regression, in particular, the goodness of fit measures. And that's all I have, so thanks for watching.